Hello and welcome to our second lesson into our introduction into organic chemistry. Today's lesson entitled Bonding and Isomerism. Our objective is to use orbital hybridization to determine the shape of an organic molecule and understand and identify different types of structural isomerism and stereoisomerism. So let's continue on with what we started with in the previous lesson, where we introduced all of our different nomenclature and our different types of formulas and our different types of functional groups, all that pertain to organic chemistry. We're going to continue that today by looking at firstly bonding, so going back a little bit back to our physical chemistry where we looked at hybridization and linking hybridization to our organic molecules. Because our drawings, when we draw our drawings, that's all just in two-dimensional space. But from our experience, we have a three-dimensional reality around us. So that can be one of the tricky things, is bridging our diagrams from a two-dimensional plane, such as a board or a piece of paper, to represent an actual three-dimensional reality, which is what the organic molecules exist in. So to do that, we've got to recap some of our understanding of hybridization. So we discussed in the previous lesson that carbon is the backbone of organic chemistry as a discipline. We concatenate carbon into millions and millions of different chains and rings and branches, and there's a magnitude of variations and combinations, which is why organic chemistry is such a versatile and interesting discipline. Now, so we're going to link, like I said, our two-dimensional diagrams to three-dimensional reality by looking at the shape, the molecular geometries of our carbon chains in organic molecules. And it's all to do with how the carbon hybridizes, because we've got our 4 valence electrons in our carbon, and it can make double bonds, single bonds, or triple bonds. And depending on where those regions of electron density, those atomic and molecular orbitals, are spaced around the nucleuses of our, or the nuclei rather, of our carbons, will dictate what geometries our molecules will have. So let's consider our electronic configuration of carbon to better understand how this bonding and geometry occurs. We've got 6 electrons, 1s2, 2s2, 2p2. So we've got 4 electrons in this valence shell, which is our second quantum level, 2 in the s, 2 in the p. So if we were to draw a carbon as a Lewis dot, we might expect 4 electrons on the outside like that. And when we have a, let's say, a carbon that has 4 single bonds, we observe each of these bonds as being equivalent to one another. So that bond is the same as that bond, same as that bond, same as that bond. So if we were to consider a energy level, well, not an energy level diagram, but if we were to do the energies of the electron subshells, we might predict a unhybridized electron diagram to look like this, where if we've got 4 electrons in 4 orbitals that can each make a covalent bond, there might be 1 in the s and then 3 in the p. However, the p being a higher energy level subshell than the s is, that would mean that these would not all be equivalent bonds, when in actuality that is what is observed. So we discussed before this idea of hybridization, where our s and our p orbitals can hybridize to make an sp3 hybridization. So this is where the orbitals merge with one another, and it's got a quarter of the character of the s and then 3/4 of the character of the p. So the energy is lower than the p orbitals in the sp3 because that s orbital brings it down a little bit. Similarly, it's higher than the s because those 3 p orbitals bring it up quite a bit. So depending on the hybridization, this will dictate the molecular geometry, because one of the fundamental principles that we keep saying again and again is that like charges will repel each other, opposite charges will attract each other. So if we have 4 regions of electron density around a carbon atom like so, and if they're all equivalent, they're going to repel each other equally, which in 2-dimensional space we might draw that like that. But in actuality, in 3-dimensional space with that extra dimension, we form a tetrahedral arrangement, which is something that we've looked at before. And we can model that very simply by just tying 4 balloons together. If we've got 4 balloons, these represent clouds, our electron orbitals, where the negative charges are going to want to get as far away from each other as they can. And in 4-dimensional space, we make that tetrahedral arrangement like that. We've got our dashes indicating that one is coming out, our wedge indicating that one is going back, and then we have two on the same plane. So if we got four equivalent electron clouds around, the tetrahedral arrangement is going to be what it forms, and that is our sp3 hybridization. However, if we want to make double or triple bonds, it can't form double or triple bonds with an sp3 hybridization because the bond angles just become too intense and the electron density just repels each other. So if we had two sp3 hybridized carbons and we formed a single bond by the overlap of two of those, so a sigma bond, we can't make a double bond because there would be too much electron repulsion to overlap another sp3 orbital. So in that case, to form a double bond, it has to go and form an sp2 hybridization. This is where our s orbital hybridizes with two of our p orbitals, but it leaves one p orbital unhybridized. So that's why it's sp2, because it's only two of the p orbitals, as opposed to sp3, where we'll overlap in all three of the p orbitals. So in sp2 hybridization, the s overlaps with two of the p's. So the sp2 has a slightly lower energy than the sp3 because it's got one less p orbital. That means that the energy is being brought down a little bit more by having more of this s orbital character. But our p orbital, which is unhybridized, remains the identical energy as the p orbital would be. Now we can model this by showing it on balloon models, where we will have this one here. So we form our three equivalent sp2 hybrids, and then we have our one unhybridized p orbital. So remember, our p orbitals have that dumbbell shape, two lobes for a p orbital. So this purple balloon there represents the two lobes of the one unhybridized p orbital. Compare that to our sp3 hybridization, where we hybridized all three to get four equivalent sp3 orbitals. In our sp2 hybridization, we just overlap the s, we hybridize the s with two of the p's to get three equivalent sp2 orbitals, and then our one unhybridized p orbital. And this gives it a sufficient geometry to form a double bond, which we will see in just a second. Because then we have our third type of hybridization if it wants to make a triple bond, where we only hybridize one s with one of the p's. So again, this will be lower energy than both the sp2 and the sp3 because it's got more s character than either of these do, and the s character is the s orbital has a lower energy. And we have our two unhybridized p orbitals. So if I were to model that, which I have done with my balloons, then we would have our two sp orbitals, where our s orbitals and one of the p orbitals have hybridized and merged to create two equivalent sp orbitals. And then we've got two unhybridized p orbitals. So one p orbital with the balloon going vertically, the other p orbital with the balloon going horizontally. Dumbbell shapes, two lobes for one p orbital. So depending on the type of bonding, depending on the type of hybridization, will dictate what the carbon will look like, what the geometry of the carbon molecule will look like in three-dimensional space. So let's look at that now in a tad more detail. We've introduced previously the concepts of a sigma and a pi bond. Let's recap them now and link it to organic chemistry. So sigma bonds form from the overlap of two atomic orbitals. Sigma bonds are lobes of shared electron pair in line with the nucleus. This is a strong electrostatic force of attraction between negative shared electron pairs and the positive nuclei of the two atoms. So our sigma bonds are our single bonds. If I were to draw a ethane molecule, carbon, carbon like that, I can do my tetrahedral geometry for both of my carbons, because they're both going to be sp3 hybridized. We form a sigma bond between each of the carbon atoms. So that's one sigma bond. Sigma bond are our single bonds. Very strong. This is an electrostatic force of attraction between the shared electron pair, the covalent bond in the middle there, and the nuclei of the two carbons being positive nuclei. So that's a very strong force of attraction between the two carbon atoms, our intramolecular forces. So let's consider the sp3 hybridized carbon with four sigma bonds, all single bonds. This will have a tetrahedral geometry. So if I were to get my balloon models again, and I've got my one sp3 hybridized carbon there, my other sp3 hybridized carbon there, well, can't talk, they would overlap and we would get our sigma bond. Sigma bonds are called sigma bonds because the bond is in line with the nucleus. We can see that is going to be the bond there, and that is in line with both the nucleuses of both of our carbons. So we can hopefully observe that there. In three-dimensional space, we've got to show the tetrahedral arrangement of both of the carbons. They're both going to have two orbitals in the same plane, and then one in front and then one behind. This is what's called our VSEPR theory, valence shell electron pair repulsion theory. That dictates what our molecular geometries will be. Each sp3 hybridized carbon atom in a molecule will be tetrahedral. Now, something that's quite important when we link this to organic chemistry is the concept that there is rotation around a single bond. If we have a single bond like that, these can rotate. These are free to rotate around one another. They're still held together by the electrostatic force of attraction between the negative electrons and the nucleus, but there's rotation. So that means that when we draw molecules, we can sort of draw them, we can draw the same thing different ways because there's a number of different, rotations that it could exist in. So if I were to draw a propane with 3 carbons and then all the hydrogens filled in, if I was to show my geometries, I would have to do this with the dashes and wedges, which is what I would do. So you show your geometry with this sort of zigzag, and this is why our skeletal formulas have that zigzag type arrangement to them, because it's representing the hybridization of the carbon. So if I fill in all the hydrogens here, one coming in, one going back. Now it doesn't matter which ones you show going in and going back because there is free rotation around these bonds. What am I doing here? Let's go one back there, one in front there, and then one back there, and then one in front there, and then one on the same plane, something like that. So if I draw a propane like this, this is exactly the same as drawing the propane with the carbon down here. Because there's rotation, because we can rotate across that bond. What have I got? I've got too many dashes. Let's do another line. So that is exactly the same as what I drew before. They're both propane because propane exists in three-dimensional space. So you've got to consider the fact when you're drawing and naming molecules that we've got rotation around single bonds, and we've also can flip and turn and do all those kinds of things. So as long as you follow the naming rules that we went through last time, and that we'll practice a lot more through this course, you'll always make sure you will always get the correct name, but you've just got to be aware that you might have to flip it or rotate it or turn it, something like that. All right, so if we were to draw this on a two-dimensional plane, as in this screen right here, we can show our tetrahedral with 2 on the same plane with the lines, 1 dash coming in front, 1 wedge, 1 dash going behind, 1 wedge coming in front. All those bond angles will be 109.5 degrees for the tetrahedral geometry. Tetrahedral geometry is our sp3 hybridized carbons, all sigma bonds. Then we've got our pi bonds, which is where we get our double and triple bonds. These are formed after an initial sigma bond. Pi bonds lay above and below the nuclei. So we saw the sigma bond being in line with the nuclei. Pi bonds are defined by being above or below. Now they require unhybridized p orbitals to overlap. We need an sp2 hybridization for a double bond, sp hybridization for a triple bond. We'll model this in just a second. The position of unhybridized p orbitals maximizes the overlaps. So, we said before that we can't form double and triple bonds with sp3 hybridization because it's just too much repulsion between the electron clouds. However, if we were to form a double bond, we would need to have a sp hybridization, an sp2 hybridization rather, where we've got our unhybridized p orbital, because this allows the geometry, if I get another model here, to overlap and form our pi bond like so. I might do another hand there. So in this case, we've got sigma bond between the two carbons, and then the unhybridized p orbitals, like that, are in a good geometry that they can now reach over, and they can merge with each other to make a molecular orbital and thus form that double bond. So the first bond is between the sp2 hybridized orbitals there. The double bond, the pi bond, is between our two p orbitals. Remember, our p orbital has two lobes, so one above and one below are both the p orbitals hybridizing. So if we were to draw that, we would end up with not a tetrahedral geometry, but our sp2 orbitals are going to be a trigonal planar geometry. Because if we look at the three green sp2 orbitals, we can see that they are all down the same plane. They're all trigonal planar, so we're going to have that 120 degrees bond angle between them. That's just due to the hybridization and the way it bonds. So if we were going to draw that, we would show that without any dashes or wedges. So if I was going to draw ethene, which is what I will do right now, if I find my marker. So I got my carbon, we form a double bond where we form the initial sigma bond, and then we form the pi bond as well, making the double bond. Sigma bond in line with the nucleus, pi bond above and below the nucleus. Then we would have our trigonal planar just like that. They are all on the same plane, so we don't need to show any dashes or wedges because they're not going into or they're not going out of the board, and we end up with that 120 degree bond angle all around. So if I get my model back, which was this one here, oh no, it's come apart a little bit. If we look at this, let's just pretend they're tied up like that, we can see that there is no balloons, there's no orbitals or no bonds going into or going out of the board. They are all on the same plane. One important property of a pi bond that we haven't discussed before is this idea that there is no rotation around a pi bonds. Pi bonds are locked in place, as opposed to our sigma bonds that we just saw. They can rotate, clockwise or anti-clockwise. Our pi bonds, which if I show you on the model, these ones are locked in place. So if we imagine this trying to rotate like our sigma bonds did, the pi bonds, the way they're bonded, doesn't allow it. And this is a really important property for something which we're about to look at in just a moment, called stereoisomerism. So we got rotation in sigma bonds, no rotation around pi bonds. So if we show this on our two-dimensional, we don't have to do dashes or wedges because it's trigonal planar. These are all on the same plane, so we can just represent the geometry like that. Our triple bonds, we might as well just have a bit of a talk about that now. Our triple bonds, very similar to the pi bonds, only they have two unhybridized p orbitals. So we've got our sigma bond between the green balloons. There are sp hybridized orbitals. Then we form one p orbital between two of the unhybridized p orbitals on each atom, and then we form the second pi bond with the overlapping of the second unhybridized p orbital. This just makes a linear molecule. It's just all in a straight line if we look at the atoms that are bonded. And same thing, no free rotation. We've got pi bonds, locks it all in place there like that. So a bit of a recap linking our hybridization, our molecular geometries to our organic molecules. Here's the task. Pause now and draw me butanol. This is an alcohol which has an OH group. I've given you a molecular formula. Let's recap a little bit from last lesson. Draw butanol and then push play now. What did you draw? If you drew something, you would have either drawn that or you would have drawn that. Which one is right? The correct answer is they're both right. They're both forms of butanol. What is limited here is I haven't obviously given enough information because I haven't been specified enough, because there's two possible structures that you could draw. An alcohol with 4 carbons, you can draw like that or like that. So this leads into an important concept in organic chemistry called isomerization. Isomerization is where we have molecules with the same molecular formula. So these are both C4H10O. If you count all that up, you're going to get that in both instances, and they're both alcohols, Only we have a alcohol group on our carbon 1 there, or the alcohol group on our carbon 2 there. So these are both isomers of butanol. They have the same molecular formula, but they have a different arrangement of atoms. We can categorize these into two main categories, things called structural isomers and stereoisomers. So isomers, we have the same molecular formula, but a different arrangement of atoms. Two main categories, structural isomers and stereoisomers. And then within these, we can break these down into even more categories, where we've got three types of structural isomers: position isomerism, functional group isomerism, and chain group isomerism. And then two kinds of stereoisomers that we're going to look at: cis and trans isomerism, and then optical isomerism. So let's look at both of these now, starting with the structural isomerism. Structural isomers are defined as molecules with the same molecular formula but a different structural formula. And there's three types that we can have: position, functional group, and chain. Let's start with position isomerism. This is where we have a molecule that has a different position for the functional group, therefore what carbon the functional group is bonded to. So the example we looked at just here, these are two types of position isomers. In this case, we've got our alcohol on carbon 1. In this case, we've got our alcohol on carbon number 2. So we can simply just name these similarly to how we named the branch chains in the previous lesson. You just put a number that dictates what number carbon it's on when you number your carbon chain. But we've got to remember that rule from last time that states that we always want to have the smallest number when we're numbering these. Here's a task. Can you pause now and have a go at drawing the following two isomers: 1-propylamine and 2-propylamine. I've given you the molecular formula, and amine has an NH2 on the end. Prop means that we've got 3 carbons. So a 3-carbon chain with NH2. See if you can get the 1-propylamine and the 2-propylamine, where our number's showing where that NH2 amine is. That will look like this. Our 1-propylamine. We have propyl, we have a 3-carbon chain. 1-propylamine, we have the amine group on carbon number 1. And then we fill in the rest of our hydrogens. Whereas with our 2-propylamine, it's going to be on carbon number 2. So very similar to how we name our branches, we just specify where the functional group is going to be. So you can see that these have the same molecular formula. In both cases, we have C3, H1, 2, 3, 4, 5, 6, 7, 8, 9, and an N. However, we've arranged them differently. We put the functional group on a different position, like so. Why is there no 3-propylamine? Why have I not asked you to draw that? Well, this comes back to the idea that molecules exist in 3 dimensions, and we have to think about the fact that we can rotate them, we can flip them. If we had 3-propylamine, where we had the amine group, let me just draw it down here, on carbon number 3, this is actually just 1-propylamine. We need to have the number to be the smallest number. So if we count from this way, 1, 2, 3, that would give us 3-propylamine, but that would be incorrect. In fact, we want to put the 1 there, 1, 2, 3. So it's on carbon number 1. So really, all 3-propylamine is just 1-propylamine. If you flip it that way, if you take that one and rotate it like that, 1-propylamine, 3-propylamine are the same thing. So there's no isomer of 3-propylamine. That's something you need to be aware of. But as long as you remember the naming conventions, always have the smallest number, then you will be good. We need to consider that isomers are in 3-dimensional space, and there is rotation around single bonds, and that we can draw the same molecule different ways because it can rotate and twist and flip. Next one is functional group isomerism. This is where we have the same molecular formula, only the structural formula means that we have different functional groups. This will change the chemical property of the molecule as different functional groups have different properties. Can you determine the molecular formulas for both these isomers, butanoic acid and methylpropanoate? If they have the same molecular formula but different structures, they will be isomers. If they don't, they won't be isomers. I've drawn up two skeletal formulas. Notice the zigzags are showing the hybridization. So what is, if this is the butanoic acid and if this is the propylmethanoate, what is the molecular formula? Pause now, work it out, and then we will check. We got 1, 2, 3, 4 carbons. So it's C4, 1, 2, 3, 4 carbons over there. How many hydrogens? We're gonna have 3 hidden hydrogens there, 2 hidden hydrogens there, 2 hidden hydrogens there, and 1 on the end. So 3 plus 2 is 5, 7, 8. H8. And then we're going to have 2 O's. What about over here? We're gonna have 1, 2, 3 hidden hydrogens there, 2, 3, 4, 5, 6, 7, 8, because this carbon and this carbon already have 4 bonds, so there's no hydrogens on that, because we know carbon only makes 4 bonds. So you can see here, we've got the same molecular formula, but we've got 2 different functional groups. We've got a carboxylic acid over here, and we have something called an ester over here. So these are functional group isomers because they have 2 different functional groups. Finally, we have our chain isomerism, which is where we have different branched alkyl groups. So we essentially have a different backbone of the carbon. Let's consider butane versus methylpropane. So if I go and draw butane, we would have 1, 2, 3, 4. If I was to draw a displayed formula, we would just draw it like that. Note that sometimes if it's not pertinent, you don't have to show the hybridization. Here I'm just showing the molecules with the displayed formula and the bonds are just like that. But I've shown the hybridization in the skeletal formula above. Compare that to methylpropane, where we've got 1, 2, 3, and then we've got a methyl group coming off like that, which would look like this. We'd have our 3 carbons and then a methyl group off the top there. Now notice here that I haven't specified that it is 2 methylpropane. That's because there's only one possible methylpropane that you can have. Because if you had 1 methylpropane, if you had a propane but you had the methyl on the carbon 1, well, you've just got a butane. That's not a different isomer. If you had 3 methylpropane, you had a methyl on carbon 3, that would also just be butane. So it's all about, if you can, communicating the information in the least amount of detail as you possibly can. So we don't have to say 2-methylpropane because there's only one potential isomer for methylpropane. You can say 2-methylpropane, but you don't have to. So we can see here, these are both C4H10 in both instances. However, they've got different structural formulas. So different branches, this is just straight, this has a methyl. They are chain isomers of each other. Here's a task for you to see if you can work out. Draw 3 chain isomers of an alkane with molecular formula C5H12. So 5 carbons alkane will start with a pentane. See if you can work out any other, or not any other, 3 other isomers that can have that molecular formula. Pause now and we will check it now. So let's start with the pentane. 1, 2, 3, 4, 5 straight chain, nice and easy. C5H12 if we were to count up all those hidden hydrogens. Then we could have the parent chain being just 4 carbons, so we have some sort of butane, and then to have that 5th carbon and the hydrogens that add up to C5H12, we could have a methyl butane. You could specify 2-methyl butane, however you don't have to, because if we put the methyl group anywhere else, we wouldn't end up with anything different. If we put it on carbon number 1, then we would just have another pentane. If we put it on carbon number 3, then that would just be a methyl butane as well, because that one and that one would be the same, they're just flipped and rotated. Then finally we could have a propane chain, and then we could have a dimethyl, something like that. So this would be a dimethyl propane. Now you could say 2,2 dimethyl propane, but you don't have to because there's only one possible way to have that arrangement. What about if you had a ethane and then you had a propyl group coming off it? 1, 2, 3. Well, that's just pentane. Yeah, it's just the same thing. What about if we had our propane and then we had the ethyl coming off that way? We'd have 1, 2, 3, 4. that would actually just be our methylbutane as opposed to an ethyl propane. Methylbutane would be the name because of the rules we discussed. We always have to find the longest parent chain. So our three types of structural isomers: position, functional group, and chain. Now our stereoisomers are a little bit different. They're a little bit more complicated to wrap your head around, but essentially they've got the same molecular formula and they've got the same structural formula really. They've got the same atoms bonded to one another. However, in three-dimensional space, those atoms are different and there's no way that you can rotate or flip it or move it to make it the same thing. Cis and trans isomerism is observed in alkenes. This all has to do with the fact that we said there's no free rotation around a double bond. Therefore, we can have a different arrangement of atoms around a double bond in our unsaturated alkenes. We refer to these as cis and trans. So, cis and trans are both Latin prefixes. Cis means on this side of, trans means across from. So if we have a cis conformation, it means the atoms we're specifying are on the same side of the double bond, cis meaning the same, on the same side of, whereas trans means they're on the opposite side, they're across from each other. What do I mean by that? Let's look at an example. I'll draw two isomers of a alkene and we'll see why these are in fact different. They're going to have the same atoms bonded to one another, however, they're going to be slightly different in three-dimensional space. So 1,2-dichloroethene. If I draw my geometry here, so I got my ethene and I've got 1,2-dichloro. So I'm going to have a chloro on both of the carbons. So I could either have a chlorine there and a chlorine there, and then these are hydrogens like that, or I could have the chlorine there and the chlorine there, and these are both hydrogens like that. So because we can't rotate this bond, because if I get my balloons back here, because there's no way to rotate that, it's fixed in place. If I have my chlorine there and my chlorine there here, if I flip it like that, they're both going to be on the bottom there. It's going to be different to that one there. If I have my chlorine there and my chlorine there, I can rotate it like that, but I'm never going to be able to have these be the same things. It's still a chlorine bonded to a carbon, bonded to a carbon, bonded to a chlorine. Same thing here, chlorine bonded to a carbon, bonded to a carbon, bonded to a chlorine. However, the arrangement in three-dimensional space, because of the lack of rotation, means that they are going to be isomers. So these are both 1, 2, why did I do a dash? These are both 1,2-dichloroethene. Can you name the cis and the trans, we'll just separate that a bit more. Can you name the cis and the trans isomers based on cis meaning the same side, trans meaning the opposite side? Which one do you think is each? We have this one being the cis. They're on the same side of the double bond. So this would be called cis 1,2-dichloroethene, whereas this one is the trans. These are on the opposite side of the double bond. So this would be our trans 1,2-dichloroethene, yada, yada, yada. So stereoisomerism, same arrangement, same atoms bond to one another, but in a different three-dimensional arrangement. Now our last kind is what is called optical isomerism. So this occurs only in a carbon atom that is bonded to 4 different atoms or groups. So that means the carbon needs to be sp3 hybridized, all sigma bonds to 4 different atoms or groups. And what this creates is it creates a non-superimposable mirror image. So you can imagine your hands are really good analogies for this. You've got a left hand and you've got a right hand. They're exactly the same. They're a palm with 4 fingers and a thumb. However, they're non-superimposable mirror images of each other. There's no way you can superimpose your hands exactly over one another, but they're identical in every other way that you could consider. What do I mean by that? Let's have a look at a diagram here. We've got 2 isomers around a chiral center. So the carbon atom in the middle of an optical isomer is called a chiral center. And you can imagine having a left-hand isomer and a right-hand isomer to use the analogy of our hands. These are also called enantiomers of each other, but not a term we need to be specifically familiar with at this point. So we have a carbon bonded to 4 different groups, and whilst these might look identical, there's no way that you can perfectly superimpose these. So let's see this with some models. So I've got two tetrahedral carbons bonded to four things, and I've shown the different four things with different colored bands. So I've got a bond in this carbon that has no band. We've got a red one, we've got a pink one, we've got a yellow one, same thing over here. So these are perfect mirror images of each other. But there's no way that I can rotate this to get the same atoms in the same places. As you can see here, we've got the yellow in the front, whereas over there I've got the red in the front. I've got the yellow behind here. So whilst they're mirror images like that, if you imagine a plane of symmetry down the middle, I can't rotate these at all to have the same groups in the same positions. They're optical isomers of each other. Same way you can't superimpose your left and your right hand on each other. So if we consider a diagram here, if we think about rotating this 180 degrees, well, that would put the bromine at the back there and the chlorine would be coming out the front here. They get the name optical isomers as they differ in how they affect polarized light. Polarized light only vibrates in one plane. Optical isomers will rotate the plane of light by equal amounts in opposite directions. A bit physicsy there, but that's how we can determine which is which, by seeing how they will rotate the polarized light. So both of these stereoisomers have the exact same atoms bonded to each other. Here we've got a carbon bonded to a fluorine, hydrogen, bromine, and chlorine. Same thing over here. However, we've got different arrangements of these atoms in three-dimensional space. And that concludes this lesson on bonding and isomerism. What have we looked at? We have looked at the shapes of organic molecules, describe and explain the shape of and bond angles in the ethane and ethene molecules in terms of sigma and pi bonds, predict the shapes of and bond angles in other related molecules. Then we looked at our isomers, describe structural isomerism and its division into chain, positional, and functional group isomerism. We've described stereoisomerism and its division into geometrical, cis-trans, and optical isomerism. Described geometric cis-trans isomerism in alkenes and explains its origin in terms of restricted rotation due to the presence of pi bonds. We've explained what is meant by a chiral center and that such a center normally gives rise to optical isomerism. And we've identified chiral centers and geometrical cis-trans isomerism in a molecule of given structural formula. Here are our tasks for this lesson. Pause now to consolidate the concepts we've looked at with bonding and isomers. Thanks as always. I will see you in the next one when we conclude our introduction to organic chemistry. Have a great day.